Specific heat capacity, understanding energy transfer in materials. Recap, heat versus temperature. Before we introduce anything new, let's quickly recap two ideas we already know: temperature and heat. Temperature measures the average kinetic energy of particles in a substance. So, if the temperature is higher, the particles are vibrating or moving faster on average. Heat is different. Heat is energy that is transferred from a hotter object to a colder object. This transfer continues until both objects reach the same temperature. When that happens, we say the objects are in thermal equilibrium. For example, if you place a cold drink in a warm room, heat flows from the surrounding air into the drink until their temperatures equalize. So remember, temperature tells us about particle motion. Heat tells us about energy transfer. Discussion: hot spoon versus cold spoon. Now let's think about a familiar situation. When you stir hot soup with a metal spoon, it quickly feels very hot. But when you use a wooden spoon, it doesn't feel nearly as hot. Why do you think that happens? Explanation: you might have said, the reason is that metal conducts heat much better than wood. Energy from the hot soup transfers quickly through the metal spoon and into your hand. Wood is an insulator, meaning it does not allow heat to pass through easily. So much less energy reaches your hand, even though the soup itself is just as hot. The metal spoon quickly reaches the same temperature as the soup, while the wooden spoon does not. Why metal feels colder? This idea also explains something else that often surprises people. At the same temperature, metal feels colder than wood. This is not because metal is colder. It's because metal conducts heat away from your hand faster. Your skin senses the rate of heat loss, not temperature directly. Metal removes thermal energy from your skin quickly, creating a cold sensation. Wood transfers heat slowly, so it feels warmer. This shows us that different materials transfer heat at different rates. Introducing specific heat capacity. Now we're ready for the main idea of this lesson: specific heat capacity. Specific heat capacity, which we usually call C, is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. The units are joules per kilogram per degree Celsius. A material with a high specific heat capacity needs a lot of energy to warm up. It also releases a lot of energy when it cools down. A material with a low specific heat capacity heats up and cools down quickly. Comparing common materials. Let's compare some real materials. Water has a very high specific heat capacity. This means it heats up slowly and cools down slowly. That's why oceans help stabilize Earth's climate. Aluminium has a moderate value. This makes it useful in cookware because it heats up quickly and evenly. Copper has a low specific heat capacity. It heats rapidly, which makes it ideal for heat exchangers and electrical wiring. Concrete has a fairly high value. It absorbs heat during the day and releases it at night, which is useful in buildings. The energy transfer equation. To calculate energy changes during heating, we use an important equation: Q equals mc delta T, where Q is the energy transferred in joules, m is the mass in kilograms, C is the specific heat capacity, delta T is the change in temperature. This equation only applies when there is no change of state, so no melting or boiling. Worked example. Let's work through an example together. How much energy is needed to heat 2 kilograms of water from 20 degrees Celsius to 80 degrees Celsius? The mass is 2 kilograms. The specific heat capacity of water is 4,180 joules per kilogram per degree Celsius. The temperature change is 60 degrees Celsius. Substituting into the equation gives us an energy of 501,600 joules. That's over 500 kilojoules of energy. This shows just how much energy water can absorb without a large temperature increase. Fill in the blanks activity. Let's check your understanding. The amount of energy needed to change the mass of a substance depends on its specific heat capacity and the change in temperature. This sentence perfectly summarizes the equation we just used. Experimental method. Now, let's see how we could measure specific heat capacity experimentally. First, we place a known mass of material in an insulated container with a heater and thermometer. Next, we supply electrical energy for a set time and record the initial and final temperatures. Finally, we use the equation Q equals mc delta T to calculate the specific heat capacity. The energy Q is calculated from electrical energy using voltage, current, and time. Analyzing experimental data. When experiments are done carefully, we get values like aluminium around 850 joules per kilogram per degree Celsius, iron around 420, water around 4,100. These results confirm that water needs much more energy to heat up than metals. When we compare experimental results to accepted values, small differences are normal due to heat loss or measurement errors. Sources of error. There are several common sources of error in these experiments. Heat loss occurs if insulation is poor. Uneven heating can cause inaccurate temperature readings. Measurement errors in mass, voltage, current, or time affect calculations. Thermal lag occurs because thermometers and heaters take time to respond. Recognizing these errors helps improve experimental accuracy. Real-world applications. Specific heat capacity is used everywhere. Engineers choose materials based on how they store heat. Car radiators use water because it absorbs large amounts of heat without overheating. In climate science, oceans moderate Earth's climate because of water's high heat capacity. In cooking, oil heats faster than water, which is why frying happens quicker than boiling. Final summary. To finish, let's summarize the key ideas. Specific heat capacity tells us how much energy a material stores per degree of temperature change. The equation Q equals mc delta T allows us to calculate energy changes during heating. Experiments can compare materials, but we must account for heat loss and measurement errors. Understanding this concept explains why different materials behave so differently when heated. If you enjoyed this video, don't forget to like and subscribe for more.